Okay, so light travels at about the same speed in a vacuum because there are no significant gravitational effects to differentiate them. We can see there is a difference in diffraction, in mass. When you shoot light through a medium, it does not come out the other side unaffected. And so we can see that, if you shine it at a prism, different wavelengths are affected differently. And so to me, I've said I'm going to make. I bought like some prisms and some lasers and stuff, and I'm going to do some of my own experiments because I'm convinced right now, and I have to unconvince myself otherwise. But basically, um, diffraction is, in my opinion, gravitational lensing, and it affects different wavelengths of light differently because they have different energies and they're moving at different speeds. And I watched a video saying that the speed of light is constant, and that light travels at the speed of causality, and that light doesn't experience time. And I'm just looking at these things and I'm saying light doesn't experience time, but we have redshift. And so I ask you, if light doesn't experience time, how? How do we have redshift? Light doesn't experience time. I'm not even going to go farther on that. Anyway, and so we know that adding more energy to an object near the speed of causality increases its speed by only a fraction, right? Something going at 0.9 the speed of light, you add 0.1 to that, it's not gonna then be going the speed of causality. Speed of 0.9 the speed of causality, you add 0.1 to that, it's not going to be going the speed of causality, it's going to be going like 0.9, I don't know, 9.1, 9.2. Like I don't even know the math exactly. But the important thing to take away is that it doesn't. The closer you get, the more energy you put in, the less difference it makes. Right, like the closer and closer you get, you can keep putting energy in, but in theory, you never actually reach that point. And so this is why I think light has mass, and so it could have a very tiny amount of mass, but it still has mass, and so it can have high energy and be moving at an extremely fast speed. And at these extremely fast speeds, right, you add more energy in, it doesn't seem to be going much faster, but it does have a lot more energy. And I think that this is an important thing to factor, because a slight difference in energy level, or a slight difference in speed, would result in a massive difference in energy when it comes to, um, this scenario. Like if you have a tiny bit of mass that's flying really fast, and say it's going, I just have some random numbers here, 0.989 the speed of causality, right? If you have another particle, right, and you give it, say, 10 times as much energy, it's not going to be going the speed of causality. It's going to be going, I don't know, like 0.98, if probably, maybe not even that, I don't know. Maybe like the speed of light is closer than that. But the point I'm trying to make is that the difference in that number, the difference in that speed would be minimal, but the energy difference would be very, very different. And so that's why I think it makes sense that light does have mass, and it's a very tiny mass, but it does have mass. And on top of that, we have wavelengths. And again, what the heck is a wavelength if light doesn't experience time? What the heck is that then? It shouldn't have a wavelength. because it doesn't experience time. There shouldn't be a high and a low point of light. It should just be light. Honestly, if light doesn't experience time, it should be a particle. It should not be a wave. It shouldn't have a wavelength. It doesn't make sense. Anyway, that's besides the point. I'm getting caught up in it. But I think that these wavelengths are important because we know that red, just in the visible spectrum, red has lower energy than blue. But we know that blue has a higher frequency. And we have a formula that says that the frequency times the Planck length, or something along those lines, is energy, right? And we basically just say, oh, well, higher frequency, higher energy. But that kind of yada yada's around the fact of why it has a higher frequency. It doesn't explain why it has a higher frequency. It is just kind of saying, well, yeah, higher frequency, higher energy. And I don't think that makes sense. I don't think that's right. I think that it makes more sense to say higher frequency because higher speed, because higher energy, because it does have mass. And we know that things moving fast, like towards the speed of light, have length contraction. We know that that's a thing. And so when we look at these wavelengths, the higher energy wavelengths have shorter frequencies because of length contraction. And I just think that this is a logical conclusion to come to. And I'm going to do some experimenting, and if I prove myself wrong, then so be it. I proved myself wrong. But I ordered some things to do some tests, and if my results work if my experiment works the way I think it could, then I'm going to be very excited. But I don't want to get my hopes up too much that that I actually could have some proof of my theories more than just me talking here. So, yeah. But what was this about? Basically, I think that that there may be some factors when measuring the speed of light, right? But I think it could be possible to find a differentiation in between. If we can find a way to calculate the mass or calculate the energy, then we can backtrack to get a speed. So what I want to do is try and see if we can set a standard, because if we can set a standard saying speed of light in a vacuum is, its top speed, and we'll say that is its highest energy, so then we'll say that that's gamma, right? And we set that speed, then we can backtrack to find a mass. If we know the energy of a gamma photon, then we can backtrack to get a mass, and then try and use that mass then, and also the energy of other known wavelengths, and just kind of backtrack backwards and get different speeds and see what those speeds are. I imagine that they're not not that different from each other, because the mass is not that different. But those are some calculations that I want to do, because I imagine if you did do that, you would end up with different speeds. And I'm curious what those speeds are, because if the speeds are drastically different, then okay, maybe there's more at play here. But if the speeds are, what we would expect to be basically insanely fast, but, still basic, like when you look at the percentages, it's like 0.999 or whatever the speed of light or something along those lines. Maybe it's slower. Or the speed of causality. I mean, I don't even know. But if we can set, a benchmark and say this is the fastest light goes. We know this. Let's see how slow it can go, right? I think that could lead to some interesting stuff. But I'm working on that, so have patience, I guess. Anyway, peace out.